Hi student, welcome back to PHY260 Chapter 4 about sound wave. Today we'll discuss part 4 of the chapter, which is Doppler effect. So, in the previous lecture, we discussed about sound or source when the source is at static position. But now, what happens if the source is moving from one point to another point? What do you think will happen to the wavelength and also the frequency of the sound? Will it change? And how do you know if there is an ambulance approaching us or moving away from us? Yes, by the sound of the sirens. When an ambulance passes by, the sirens will hurt quite a large pitch compared to when the ambulance leaving us, you will hurt a lower pitch. This is a common physical demonstration of Doppler effect. So what is actually Doppler effect? Doppler effect is an increase or decrease in frequency of sound wave as the source and the observer move towards or away from each other. Example, as given, the effect causes the sudden change in pitch noticeable in passing sirens. So let's look at the video. What happened to the sound heard by Ali and Amran as the ambulance moved towards Amran? Yes, Amran will hear high pitch from the sirens, while Ali will hear a lower pitch. This only happens when the source, which is ambulance, is moving. So why does it happen? First, you need to differentiate between stationary source and moving source. Remember, when the wave of sound travel, it will travel in 3 dimensions. As the object is static, the wavelength of the sound wave remains the same. While if the source is moving, the wavelength is changed respect to the direction of the motion. So we have 2 examples here. One is antenna, another one is airplane. Both produce sound. But what happened to the antenna? Because of the antenna is static, the wavelength is constant. But for the airplane, since the airplane is moving, what happened to the wavelength produced? The wavelength will shift it. There is a part where the wavelength is shorter. There is a part where the wavelength becomes longer. So how does it happen? Okay, we assume that there is a source that emits a wave or a sound wave, and then the source will started to move to the right. So what happened here is, when the source is moving, at the same time, the source still emits another frequency or another wavelength. Now, the 2 circles are no longer concentric anymore, but one of the sides are closer together and the other side are further apart. The wave will continue to shift to the right, and based on this formula V equal to F lambda, we assume that the speed of sound wave remain constant. So what happens is, when the wavelength becomes shorter, you're going to produce high frequency of sound. And when the wavelength longer, you're going to produce low frequency of sound. So that explains why does the two different observers will hear a different frequency. Let's say the source is moving to the right or moving towards the front observer. So the front observer will hear a higher frequency due to the wavelength is shifted towards him. So the wavelength becomes shorter. While for the back observer, it will hear a lower frequency due to the wavelength become longer. Okay, so now what if the source is static? Can you guess what are the frequency heard by both observer A and B? Yes, if the source and both observer are static, both A and B will hear the same frequency. And now if the source is moving, so which one will hear a higher frequency? If the truck is moving to observer B, of course observer B will hear higher frequency compared to observer A. Doppler effect derivation. Doppler effect derivation, when the source is at rest or fixed position, d is equal to lambda, or the wavelength will be constant for every crest emitted. When the source is moving, the wavelength is different for the different crests emitted. Doppler effect derivation. How to calculate the frequency heard by the observer when the source is moving towards him or her. First, need to calculate the new wavelength prime. The wavelength prime is equal to the distance at rest minus with the distance when it's moving. Replace d source moving with v multiplied with t. Period is equal to inverse of frequency, replacing f with v over lambda. Therefore, lambda prime is equal to lambda times 1 minus v source divided by v. The new frequency is equal to v over lambda. And replace the lambda so that the f prime is equal to f times v source divided by v minus v source. Doppler effect equation. From the derivation, we can use the same method to calculate different cases by just using one equation. F prime is equal to F in a bracket V plus minus V naught divided by V plus minus Vs, where F is the frequency of sound, V is the velocity of the sound, V naught is the velocity of the observer, Vs is the velocity of the source. But how do you know when to use plus or minus for V naught and Vs? Don't worry, we're going to discuss in detail every single cases. So there is 4 basic cases for Doppler effect. First is when the observer moving towards the source and the source is static. Second, the observer move away from the source. At the same time, the source is static. Case number 3 is what happens when the source is moving towards the observer and the observer is static? And the last case is when the source is moving away from the observer and the observer at the same time is static. Case number 1 and case number 2 for Doppler effect. For case number 1 and number 2, the source is static, or in other words, Vs is equal to 0. So started with case number 1, observer moving towards source. Using the general equation f prime equal to f in a bracket v plus minus v naught divided by v minus plus vs. So in these cases, we will eliminate vs or we will cancel vs because we know that the source is at static. Vs is equal to 0. So we're going to focus on v naught. So common sense, what happens if you are moving towards the source? Of course, you're going to hit a larger frequency as you moving towards the source. So to get f larger, your v naught supposed to be positive. So when v naught positive, f prime appear higher when the observer towards the sources. So you will get f large. Second case, when the observer is moving away. Using the same basic equation, f prime equal to f in a bracket v plus minus v naught divided by v plus minus vs. So in these cases, the source is at static. Therefore, vs cancel out. So now we're going to focus on our v naught. What happens when an observer moving away from the source? Of course, whenever you move away from the source, you will hurt the frequency become lower and lower. So to get a small value of frequency, your V naught must be negative. So when V naught negative, F prime appears lower when the observer away from the source. Case number 3 and case number 4. Doppler effect when the observer is at static. So when the observer is static, please keep in mind your V naught must be equal to 0. Using the same equation, F prime equal to F in a bracket V plus minus V naught divided by V plus minus Vs. So when the source is moving towards, V naught is equal to 0. So we only have V divided by V minus Vs. So what do you think will happen to the observer when you have a source moving towards the observer? Of course, the observer will hit a larger frequency. So to get a larger frequency, what happened to the denominator? The denominator must be smaller. To have a smaller denominator, your Vs must be negative. Same difference when the source is moving away. As the source is moving away, of course, the observer will hit a smaller frequency. So to get a smaller frequency, your denominator must be large. So when your denominator is large, it will affect the frequency will become smaller. To get a larger denominator, your Vs must be positive.